Okay, what we need to understand has to do with correlation. That's what scatter plots are all about. How closely related to the data is our line, or how strong is the data that we're trying to connect. So yesterday we talked about a scatter plot. We showed what a scatter plot looks like. You've got these points scattered about. But these points are following a pattern. We can draw what's called a line of best fit for this data. Notice that the line of best fit does not touch every data point. It may not touch any of the data points. But what it is the, as much as possible, the same distance from every point. As close to every point as we can possibly get it. Now, it's not going to be the same distance, but on average, we're getting it close as we can. This is also called a trend line or a prediction line or a regression line. Now, when it comes to using it in these different contexts, they may say, all right, what trend is this data following? And in the stock market, they talk about trends. All right, this stock is trending upwards. So you may want to hold on to it for a little while before you sell it, because the price might go higher. So you want to sell it when it's at its highest possible price. So that's the trend. All right. Prediction. Let's say that I want to know the value when so-and-so, such and such is at 100. Well, maybe I don't know what this value is down here, but I can make a prediction by using the line. So at 100, whatever that 100 means, it doesn't really matter. I can say, all right, if there are 110 cans, how much weight would that be? The weight would be down here. All right, so I go across and down, and I say, oh, it might be 10 pounds. It'd be less than that, but. So you can use your line as a prediction tool. And then the regression line. Regression is the formal name for the line of best fit. It's what the calculator is going to do for us here in just a minute. Now, we need to understand the types of correlations that are out there. I can't remember if I showed you this yesterday, but you've seen it before. There are three types of correlations. Yes. This is a positive correlation. Now we say correlation, correlation. They are related. These two things are related to one another. So if there's a positive correlation, that means the line of best fit has a positive slope. They're trending up to the right. If we have a negative correlation, the points, the data values, are trending down to the right. So there's a negative slope for our line of best fit. And then you have no correlation. And this means that the data points are everywhere, all over the place, no pattern, no trend. And so this would be, there is no line of best fit that works for this data. Now, there is also something called a correlation coefficient. This correlation coefficient is the letter R, lowercase r. The correlation coefficient follows a range. In other words, the correlation coefficient can be from -1 to 1. From -1 to 1. Now, if it's close to -1 or 1, it has a strong, if it's close to -1, it has a strong negative correlation. What does that mean? That they are very, very, very much related to one another. Connected. The two categories that you're dealing with are very connected. But they just create a negative slope down to the right. All right? If it's close to 1, that would be a strong positive correlation. Okay? Now, if it has 0 for its correlation, guess what? That's no correlation. So if I'm close to 0, is it strong or weak? It's weak. The closer I get to 1 or negative 1, the stronger that it is. So what's the difference between negative 1 and 1? One's, say it. Say it. No. One's positive, one's negative. They're the same, listen, they're the same kind of strength. It's just that the slope of one is positive, slope of one is negative. For example, let me put a couple of these things up here. The closer the data values are to the line, the stronger that it is. Okay, which is a stronger correlation? The first one. Okay, so the correlation coefficient for this might be 0.95. It's almost a straight line. All right, the correlation coefficient for this one might be 0.4. Is that strong? No. There is some correlation there. It's just not very strong. These are both positive. So let's take a look at a couple of negative ones. What would the correlation be here?
Like 9.5.
Maybe it's negative 0.9. All right, what about this one? Negative 0.7, negative 0.6, whatever, you just kind of give an estimate. And the reason we know that is because these points are very close to the line. These points aren't as close to the line, so this is not as strong. The closer you are to the line, the stronger the correlation is. So if it's scattered everywhere and it's no correlation, then R equals 0. All right, so let's take a look at your packets. So on the packet from yesterday, the last page, we had line of best fit using the calculator. Use the table below to answer the questions about the population P in millions in Florida. Our directions say, use the table below to answer the questions about the population P in millions in Florida. So I've got two parts of this table. I've got the year and I've got the population. So how many lists do you think we're going to use in our calculator? 2 lists. 2 lists. On the top here, you might want to write 2 lists. All right? You've basically got your X list and your Y list. Because every table has an input value and an output value. You just have to make sure that you're consistent. In other words, the X list needs to be the first list. So in this case, the X list is our T value. This is our input. The input needs to be your first list. This is the output. So, year 2002 gave me this population. Year 2003 gave me this population, and so on. All right, so the best fitting line for the data is Y equals 0.46x minus 904.46, and the correlation coefficient is 0.99. I'm going to show you how to find that right now. So here's what we're going to do. We're going to go to our calculator. Okay, we're going to clear it out. We're going to go to our list. So press Stat, press Enter on Edit. Clear that list. So go up to L1 and press Clear and then Enter. So now we have empty list, list 1 and list 2. All right. Does everybody have empty lists? Let me see it. So we're going to plug in the years in list 1. So we're going to do 2002. Enter, just like we always do. 2003, enter. 2004, enter. 2005, enter. So we've got our years entered into list 1. When you've done that, then you're going to enter the population into list 2. So 16.4, 17.0, 17.4, 17.8. When everybody has those 4 items in each list, look up. Okay, so again, you got 2 sets of data. You got list 1, you got list 2. List 1 is your input. That's your X value, basically. In this case, it's T for time or years. And then you've got your output. In this case, it's population. All right, the next thing that you press is stat again, calc. Are we going to do 1 or 2 variables this time? 2. We're going to do 2 because there are 2 lists. There are 2 variables, input and output. So we're going to actually time out. No, we're not going to do 2 variables. There are 2 variables, but we want to do a linear regression. So scroll down until you see linear regression, AX plus B. Do you see that? Number 4. We're going to go down to number 4, linear regression, AX plus B. AX plus B is slope-intercept form. So we're going to press enter on that. Now, X list should be L1. Y list should be L2. Is that what you've got? Okay. Go down to calculate. Press enter. All right. So we see what our A value is and we see what our B value is. So AX plus B is just all it is our slope-intercept form. Now, is that exactly what they have? Yes. It's exactly what they have. They have 0.46x minus 904.46. So you're going to be required to take the A and B value and plug it into y equals AX plus B. If I ask you what the equation is, right? They gave you the equation on this paper. It is right here. But I will not necessarily give you the equation on the test. You're going to have to find it like we just did and take the A and the B and plug it into the equation AX plus B, right there, so that it looks like what they've got. Okay? Now, what did we not find yet? We did not find the correlation coefficient yet. So we have to learn how to do that. There's a setting that needs to be changed in your calculators in order for it to do that. So here's what we're going to do. We're going to go to well, you can see my calculator. All right, we're going to press second and then 0. Second, 0. That takes us to a catalog. We have to scroll down until we get to the D's. These are in alphabetical order. We're going to go to the D's. And there is a D that says diagnostic on. Does everybody see diagnostic on? You need to turn that on. So we're going to press enter on diagnostic on. When you do that, you're going to press enter again. And it's going to say done. So diagnostic has to be turned on. Is everybody's diagnostic on? Okay, now we're going to go back to where we just were. We're going to press stat, calc, linear regression, AX plus B, press enter, go down to calculate. Okay, now, not only do you see A and B, you also see R squared and R. We don't care about R squared. That's the correlation coefficient squared. We don't care about that. All we care about is R. Is it the same thing as your paper says? 0.99. Yes, they just rounded. And you're going to round to 2 decimal places. So yes, we got it right. Now, using this model, what will be the population in 2020? So now we're going to use our line of best fit formula to make a prediction. So what am I going to plug 2020 in for, you think? X. So here's what we do. Y equals 0.46 times 2020 minus 904.46 equals. All right, so you're going to go to your just regular calculator function. Just press clear. You're going to plug in 0.46 times 2020 minus 904.46. And guess what? 904.46 is your y-intercept. And press enter. What do you get? 24.74. So what is this telling us? What is this telling us about the population in the year 2020? 24.74 million. Okay? That's in millions. So 24.74 million people living in this town or this state, whatever, in Florida, in the year 2020. So we're able to use our equation that we just determined based on the data. This is our line of best fit. We're able to use that line to make a prediction about the future. All right, so let's do another one. What will be the population in 2050? So we do y equals 0.46 times 2050 minus 904.46. And what do you get? You can actually just use the same equation. So I use my same format, go up to where we plugged in 2020, press enter, and then change it to 2050. Press enter. What is it? 38.54 in 2050. So I don't even need my chart. As long as I have the line of best fit formula, I can make any prediction. That's why this is so useful. All right, now let's do the next one. Do the same thing we did before. You're going to use the table below to answer the questions about operating costs and thousands of a small business from 2000 to 2007. So go to your Stat button, go to Edit, clear your list, and plug in the new data. And we're going to confirm that it is what they say it is. Okay, so I plugged in my data into list 1. Now I'm going to plug the data into list 2. Make sure that your two lists have the same number of data items, because if you don't, it's going to give you an error. Okay, so once you've plugged in the data into both lists, we've already turned our diagnostic on, so it should give us the correlation coefficient. So after you've plugged it in, you're going to press what button? Stat. And then you're going to go to Calc, and then you're going to go down to number 4, Linear Regression. Press Enter. Go down to Calculate. Press Enter. And it gives you everything you need. So let's confirm that our A and B values are the same as what they've got. Yes, they are. A is 0.67, B is negative 1341.03, and the R value is 0.97. So this is a positive correlation. It's almost 1. That means it's a very strong correlation between years and operating cost. So in this model, what will be the operating cost in 2015? So we're going to take our equation, y equals 0.67 times 2015 minus 1341.03. And we plug that into the calculator. So 0.67 in the calculator times 2015 minus 1341.03. And what did y'all get? 9.02, and that is in thousands. So $9.02 thousand, which is $9,000 and a little bit of change. Okay? All right, so you can do the same thing for Part B if the year is 2035. And then we're going to skip that and we're going to go to Part C. Because Part C is done a little bit differently. It says, what year will the operating cost exceed $10,000? So what does that $10,000, what value does it represent? The X value or the Y value? It represents the cost, which is what value? The Y. So we're going to plug in 10 for Y in our equation. So it's going to be 10, and we need the cost to exceed $10,000. So that means we want the right side of this equation to be greater than the left. So 10 is less than 0.67x minus 1341.03. So instead of plugging in for x, now we're plugging in for y. And we just solved this equation. So I need to add 1341.03 to both sides. So that gives me 1351.03 less than 0.67x. The last step is to divide by 0.67. So once I've done that, 1351.03 divided by 0.67 gives me the year 2000. X is greater than the year 2016. Now, what year is greater than 2016? 2017. So, in what year will the operating cost exceed 10,000? You can kind of say this two ways because it's within the year 2016. So you can say in the later part of 2016, or you can just say 2017 since we weren't going in half years. All right, so it's okay if you say 2016 or 2017. As a matter of fact, if you just say 2016, 2017, in that range is when it's going to happen. Okay, so now if you were given a multiple choice test on this, you would choose whatever the best answer would be. And the best answer in this case, it would probably be within the year 2016, so you probably want to choose that. So, this worksheet dealt with linear regression. We learned how to find basically the slope and the y-intercept, which was A and B respectively, in order to make our line, our prediction line or line of best fit, our regression line. Okay? And then we can use that line to make predictions about the future. So this is what we're going to be dealing with still in the next couple days.